All right, let's dive in. Today, we're going to talk about two components that go way beyond simple resistance, the two parts that really bring our circuits to life, the capacitor and the inductor. These guys are the secret sauce in pretty much every piece of tech you own, so let's figure out how they actually work. So, to really get why these components are so special, we've got to start with what we already know, right? The good old resistor. We know its job is to resist the flow of electricity. But what can it do? What are its limits? What are the crucial jobs in a circuit that a simple resistor just isn't built for? And that question? Well, that's exactly why we're here. To build the incredible technology we all rely on. I'm talking about everything from your phone's camera flash to the entire power grid. We need to do more than just slow down current. We need components that are dynamic. And here's the breakdown of what a resistor just can't do. It can't store energy for later. It just burns it away as heat. It doesn't care if a signal is steady or changing. It treats them all the same. You know, it's kind of a one-trick pony. It's a totally passive, unchanging element. And if we want to build smarter circuits, that's just not going to cut it. Okay, so let's meet our first hero, the capacitor. Its superpower is storing energy. You can think of it like a tiny, rechargeable battery that can charge up and then, bam, discharge incredibly fast. Now, the formal definition talks about the relationship between charge and voltage. But here's the part you really need to remember. It holds its energy in a pure electric field, not a chemical reaction like in a battery. And that single fact is what makes it so mind-bogglingly fast and efficient. And physically, it's almost laughably simple. It's just two conductive plates with a little gap, an insulator, between them. The best analogy is a water tank. Voltage is like the water pressure pushing into the tank. The capacitor stores that pressure as potential energy, just waiting to be released in a sudden, powerful burst. Okay, don't let the calculus here scare you off. That little dV/dt part, all that means is the change in voltage over time. So the whole equation is just a fancy way of saying that current, IC, only flows when the voltage is actively changing. The second the voltage holds steady, that term becomes zero, and the current just stops. Dead. And this is how you figure out how much energy it's holding. The stored energy, W, is based on its capacitance, C, multiplied by the voltage squared. Now, that squared part is a huge deal. It means if you double the voltage, you don't just get double the energy, you get 4 times the energy. It ramps up really, really fast. So, what does this all mean in a simple circuit with a battery? Well, once the capacitor gets fully charged up by that steady DC voltage, the voltage across it stops changing. And as we just saw in the equation, no change in voltage means no current. It basically becomes a break in the wire, an open circuit. Now let's meet our second hero, the inductor. And if the capacitor was all about storing voltage, the inductor is its perfect mirror image. It's all about the current, and more specifically, it absolutely hates any change in that current. And here's its formal definition. You're going to see that parallel to the capacitor again. The inductor is defined by the relationship between current and something called magnetic flux. But here's the key. It stores its energy in a magnetic field, not an electric one. Physically, it's usually just a coil of wire. That's it. My favorite analogy for it is a big, heavy water wheel in a river. It takes a huge push, that's our voltage, to get that wheel spinning, which is our current. But once it's spinning, it's got momentum. It fights any attempt to slow it down or speed it up. It just wants to keep that current steady. And check it out. The inductor's main equation is a perfect mirror to the capacitor's. A voltage, VL, only shows up across the inductor when the current IL is changing. That DIL over DT just means change in current. So if the current is steady, that whole term is zero, and there's zero voltage across it. The energy formula also mirrors the capacitor's. The energy, W, that's stored up in that magnetic field is half the inductance, L, times the square of the current running through it. So just like before, more current means way more energy. So back to that same battery circuit. What's the inductor doing? Well, once the DC current from the battery gets flowing and evens out, there's no more change, and that means there's no voltage across the inductor. It just acts like a plain, simple piece of wire, a short circuit. This is absolutely critical for things like power supplies that have to deliver smooth, steady current. Okay, now that we've met them on their own, let's put them side by side, because this is where their amazing complementary relationship really shines. They are pretty much opposites in every single way. So here it is, the big picture difference. The capacitor hates sudden changes in voltage and stores its energy in an electric field. The inductor, on the other hand, hates sudden changes in current and stores its energy in a magnetic field. They're the yin and yang of energy management in electronics. And this table just lays it all out so perfectly. Electric field versus magnetic, reacting to a change in voltage versus a change in current, acting like an open circuit to DC versus a short circuit. And that last point is so important. A capacitor's voltage can't just teleport from one value to another, and an inductor's current can't either. They're the great smoothers of the electronics world, each ruling their own domain. But this whole duality thing isn't even the end of the story. Inductors, specifically, have this one amazing property that lets them influence each other without ever touching. And this is where things get really cool. This property is called mutual inductance. It's all based on the fact that an inductor's magnetic field doesn't just stay politely inside its own coil, it radiates outward. And if another coil happens to be nearby, it can feel that field. So let's walk through it step by step. We send a current through our first coil. We know this creates a magnetic field. Now, some of that field naturally leaks out and passes right through the center of a second coil that's just sitting nearby. Now, here comes the magic. If we change the current in that first coil, its magnetic field changes too. The second coil sees this changing magnetic field, and because of the laws of physics, that change creates a brand new voltage in the second coil, seemingly out of thin air. This isn't just a neat trick, it's the fundamental principle behind every transformer and even the wireless chargers for our phones. So, as we've seen, capacitors and inductors are not just boring passive parts. They are dynamic energy managers, storing it, releasing it, smoothing out signals, filtering noise, and even interacting wirelessly. They are the foundation of everything from radio to computing, which leaves us with one final thought. As we get even better at mastering these fundamental forces, what unbelievable new technologies are they going to unlock